for low energy states, 35 minutes, and then we have 5 minutes for Q&A. And then hands up after 30 minutes.
All right, thank you. Can you hear me well?
No.
This works. This turn on. I don't think it's working. Okay, I'll speak loud. Okay, now it's working. All right. Okay, so this talk is about quantum algorithms for the specific problem of simulating quantum dynamics. There is this low energy states in the title. The things will become more rigorous as later in my talk. But I'm hoping to give you a glimpse of where the advances on quantum simulation algorithms in the last few years to hopefully make quantum simulation closer to reality. And in contrast to other talks, this is going to be more on the technical side, but I'm still hoping that you'll get a gist of what are the most useful techniques we are thinking about these days. All right. So what is the setting for quantum simulation at the high level? The idea is the following. We have a quantum system. That quantum system is modeled by some Hamiltonian that is presented to us in some way. And the goal is to use a quantum computer to simulate its dynamics and obtain, for example, some time-evolved property, simulating the Schrödinger's equation. So one way of solving this problem is by actually trying to prepare the evolved state on a quantum computer. I mean, this is not the only way one might think to go about it, but it's one possible way, and this is what the standard problems on quantum simulation, Hamiltonian simulation tackle. And in particular, the end goal would be to provide some sort of quantum algorithm, maybe a quantum circuit, a sequence of quantum gates that allow us to prepare such a state, the evolved state. So that's the generic setting here. And you might ask why this is important. Well, we hope or believe that by doing so, we'll enable the solution to numerous open problems in chemistry, many-body physics, high-energy physics, and so on. Of course, classical algorithms are highly advanced, so the competition here is very high. And for that, it's important to come up with fairly efficient Hamiltonian simulation, quantum simulation techniques. There's another interesting point that quantum simulation appears as a key subroutine in many known quantum algorithms, like solving linear systems of equations. So that is not that surprising, since this seems to be a natural problem for quantum computers to address, that the most important quantum algorithms somehow rely on Hamiltonian simulation, quantum simulation. It appears to be an extremely hard problem for classical computers, at least in the worst case, while this is a more natural problem for quantum computers because we are trying to address inherent properties of quantum mechanics. We do believe also that this type of problems will offer eventually an exponential quantum speedup. And in terms of complexity theory, what I mean that this problem can be shown to be BQP complete. It's one of the hardest problems a quantum computer can efficiently solve. For those of you that were at John's talk yesterday, probably you can skip the slide, but Feynman was one of the first proposers of a quantum computer, indeed, for tackling this specific problem. And if you want more details, you can listen to John's talk yesterday or look at his notes, which are available online. All right, so what is that we know now? Well, for the last 3 decades or so, we have gained a lot of evidence that quite likely quantum simulation problems will one day be solved with fault-tolerant architectures. We need fault-tolerant devices, perhaps with millions of qubits or so, in order to solve some interesting problem instances. To this end, we developed some fairly efficient tools. Formulas is a standard technique. These are Trotter Suzuki, where I'll explain more what they do. More recently, we came up with these ideas of linear combination of unitaries, trying to implement some Taylor series approximation to the evolution operator and quantum signal processing. Even though we have fairly efficient techniques and can be proven to be optimal in several scenarios, we still would like to improve the runtimes of these quantum simulation algorithms as much as possible. By doing so, we will be able to tackle problems of larger sizes, and this is quantum simulation problems closer to reality. So quantum simulation, Hamiltonian simulations is indeed a very active area of research these days. You might think that Hamiltonian simulation, simulating quantum dynamics is also one problem that might be tackled with these NISQ devices. There's certainly many interesting questions one can ask. Which problems we can address with these devices? Are these relevant instances? Can they also be classically simulated or not? Well, unfortunately, I would say that we are still not know much about the answer to these questions, and it seems to be a challenging problem, even for these devices. So we might need to move towards an early fault tolerant or full fault tolerant area in order to solve interesting examples. So there's more motivation for seeking further improvements to the Hamiltonian simulation algorithms that we know. And for example, we do know that sometimes we can improve the runtimes by considering certain structures of the problem, like locality of interactions and so on. Under those conditions, we might be able to do better than the worst case complexities for these approaches. For example, locality would be one type of structure that can be exploited, or other symmetries of the problem. But you might also ask yourself, like, is there any type of improvement that we can achieve whenever the states that we are evolving are states of low energy? Okay, so I make these terms more formal later on. But where this problem might be interesting, well, perhaps, for example, in adiabatic quantum computing, you are interested in involving low energy states, right? And solving some more complex problems. Can we have some sort of improvement to the runtime of Hamiltonian simulation because the states are of low energy? Or even in quantum field theories, low energy states appear all the time in quantum field theories. Or for computing, for example, ground state properties of a many-body system or some molecule or something like that. So if we can achieve some improvement under this low energy assumption of the initial state, then those improvements would be useful and hopefully practical. So this talk will be about this, about how to use this structure, additional structure, about this property of the state whenever it's low energy, and trying to simulate its dynamics. And see whether we can improve upon the generic complexity bounds that we have for methods that apply for all Hamiltonians and states. So the main question I try to address is whether we can improve the runtime of quantum simulation algorithms if we are evolving states of low energy. And I should point out that there is something that we call the no-far forwarding theorem that applies generally, does not make this assumption on the energy of the initial state, but it does say that the runtime of Hamiltonian simulation algorithms should roughly scale at least with evolution, physical evolution time that you basically want to simulate times some energy scale of your problem. This is a lower bound, meaning that there's not going to be a Hamiltonian simulation algorithm that can do better than this. But the question here is whether this extra additional assumption about the low energy would enable better methods than what we have, given that we know, for example, that that assumption might be satisfied up there. So, very informal summary of results of what we achieved is that if, let's say, we have some quantum system here whose dynamics we want to simulate. That system is modeled by some Hamiltonian, and this is a spectrum of the Hamiltonian. And let's assume now that our initial state, say 0, is supported in some low energy region. And by low energy, basically what I mean is that this delta here, the largest eigenvalue, basically the largest eigenenergy in the spectrum, is much smaller than the full spectrum of the Hamiltonian. So under that condition, and if the problem is a problem where we want to prepare the evolved state after some time t, it is indeed possible to improve the runtimes of product formulas and techniques like quantum signal processing under this low energy assumption. So roughly speaking, what's going to happen is in the complexity of those algorithms that depend on the full energy, the range of energy scales of your problem. Some of those parameters that appear might be replaceable by this low energy factor. Okay. Now, for achieving these improvements, I'll explain that we will need to have certain form of access to the Hamiltonian. So the Hamiltonians have to be presented to us in some specific way in order to achieve this type of improvement. If the Hamiltonian is not presented in that way, it turns out that we can prove that no improvement is possible. Okay? So this was an open question for some years in the field, whether there's always a possibility of improving the runtime under this low energy assumption. Well, the answer here is that it is possible, but only whenever the Hamiltonian is presented in a particular form that I explained. All right. So where do we even expect some sort of improvement, right? I mean, that might be one of the first questions you have to see ourselves. Well, it turns out that the dynamics in this low energy sector is going to be slower, right? So when we simulate a quantum state, and for example, we do some sort of spectral composition of that state, what it does is it acquires a phase, and that phase depends on time and depends on the eigenvalue, depends on that frequency. If you're in the low energy sector, that phase is going to accumulate slower. So in that sense, it seems like because the frequency of this oscillation is slower, well, there is some hope that Hamiltonian simulation approaches to simulate the dynamics, the slower dynamics, are going to run more efficiently. Complexity typically depends on roughly on what is the number of oscillations we need to simulate. So that is going to be true, again, under some assumptions on the presentation of the Hamiltonian, but we'll prove that this view only applies if those assumptions are met, and if they are not met, and unfortunately no improvement is possible. So the rest of the talk is going to follow primarily these two works with my collaborators, Burak Sahinoglu, Quantum, and Alexander Sulakapa, who's been at Google and is a student at MIT with Adam Harvard. So if you want more details, this could be the main reference you have to check. So what I'm going to talk about next is try to formalize this Hamiltonian simplification problem a bit more, show what type of improvements you can obtain by using these two standard techniques, formulas and quantum singular value transform. And later in my talk, I'll explain these no-go results for generic improvement and why you're going to expect to do better than the Hamiltonian simulation algorithms that we developed. All right. So what is the Hamiltonian simulation problem more formally for low energy states? So the goal is the following. We are given some Hamiltonians presented in some way, again, that, for example, acts on n qubits. I'm thinking of qubits just for simplicity, but it could be any quantum system. There's going to be a low energy delta, right? And some evolution time t, and some precision parameter. So the goal here would be to construct a quantum circuit that implements this mapping, basically takes the initial state Z0, and basically this would be the quantum circuit, and it maps it to some state, which is the evolved state at some time t within some precision error epsilon. And we want this constraint on the difference of the states to be epsilon as long as the state, the initial state, is a low energy state. And by that I mean that the state as projected in the low energy subspace basically is supported in that low energy subspace. So this pi of lower or equal than delta would be like a projector on all eigenvalues below some delta. So we want this condition for all states in the low energy sector, and we want to find such a quantum algorithm that implements this type of mapping or approximation. So this is kind of like the picture you might want to have in mind. We want to implement this box, which is the evolution operator, but we want to do that with a quantum circuit and approximate it within some epsilon. So the quantum circuit would be composed of gates and perhaps other unitaries that we call them oracles or black boxes that gives us information about the Hamiltonian. The complexity would be, for example, what is the number of gates or what are the number of these black box calls that we need, and we want to optimize that. All right, so how to do Hamiltonian simulation in low energy subspace using product formulas? But product formulas appear in many of these Hamiltonian simulation problems are the method of choice in many cases. The way that they work is, again, we have our n-cubed system, we have our Hamiltonian here for simplicity as a sum of two terms, right? But it's more complex. Maybe it's just a sum of like operators acting locally on these spins, or like two local operators and so on. So we have some sort of presentation of this. And product formulas, what they try to do is to approximate this evolution operator by interleaving short-time evolutions under each of the terms of the Hamiltonian. This is a fairly simple concept. And the assumption here is that each of these small time evolutions with each of the terms is not too difficult to implement. So if U of t here is our evolution operator, what we want to implement, what product formulas do is they split this big time t into segments of shortened time, and a product formula of order p could be something that approximates the evolution operator for that short time s within an error which is of the form js to the p plus 1. So j here is some norm of the terms that appear in the Hamiltonian. Because the error here is at an order which is 2 or higher, then it turns out that you can always choose your S to be small, sufficiently small, such that the errors don't accumulate that much when you do this short time sequence of short time evolutions or short time approximations at each of the steps. So we want to pick that S such that the evolution operator is going to be approximated by these short time evolutions of product formulas within some error epsilon, right? But the condition applies, for example, in this case, to any state. There's no condition on the initial state. So it turns out that there's various methods to empirically estimate what the error of the product formula is. And if you run some small scale simulations and look at those errors, then for certain Hamiltonian systems, then you can see that the error actually does increase with the energy scale of your problem. Okay, so these are a few numerical simulations for some Heisenberg model, and where they basically show that if n refers to some energy scale, basically the quantum number of your eigenstate, then as you increase your n, the errors become larger and larger. So there is some sort of hope, at least for systems like this, that when you run product formulas under the low energy assumptions, you are going to have a better error scaling, hence a lower complexity for your algorithm. And that is indeed true, but again, under some additional assumptions in the Hamiltonian. So what is that we proved in that paper? Well, that essentially there is an improved error bound for product formulas and local Hamiltonians. So this is standard bound. And what we can show is that rather than considering the full energy scale of your Hamiltonian, we can replace that by some sort of effective low energy norm. Okay, so this is what we call delta prime. And as long as this low energy norm is much lower than that large energy scale, then this improvement follows. We have smaller errors and hence better complexities. All right, so in particular, if the Hamiltonians are like cubic Hamiltonians, which are local and of constant degree, one can show that this low energy norm, delta prime here, it depends on the initial low energy of your state, plus some other factors, and these other factors depend on the parameter S of the evolution time and so on. But the idea is that basically what it proves is that if this delta, for example, does not depend on the system size, as would the full scale of your system, then this delta prime might be much smaller than that coefficient J that appears there, and hence an improvement. So this is a table. Of course, you're not going to remember this, but basically what we are trying to show here is that with this low energy simulation technique, you can be the best methods based on product formulas that apply generally and that still use properties of locality and so on. Again, and this low energy condition. So this is the order notations. These are asymptotic scalings. So very quickly, how is that we prove this? Well, essentially what we've done was to define some low energy operators, right, by projecting them into some low energy subspace, and then try to find an approximation to the evolution operator by applying these low energy evolutions using these low energy effective operators. Now, the challenge here is that while you now have this formula with effective operators, these effective operators they're complicated in principle because we are doing a big projection, and hence we don't really know how to implement evolution under each of those. So what the proof does is basically states that evolving with the low energy operator is similar to evolving with a full Baire operator, and you don't introduce much error by doing so. So to prove this, I mean, the key part of the proof is that we can show that for small times, if you are in the low energy sector, that is your initial state, for example, and now you evolve with one of the terms of the Hamiltonian, yes, you're going to leak outside this low energy space, but the amount of leakage is exponentially suppressed. Okay, this is what we call a leakage lemma in our paper. So on one side, we have this leakage error that is going to go down exponentially as we go to higher and higher energies because the support of the state is going to decay exponentially. At the same time, we have this other Trotter error that is coming from the product formula, which is becoming larger and larger as our effective operators become larger and larger because their norm themselves are getting towards closer and closer to the full norm of the Hamiltonian. So it turns out that this is kind of like an optimization problem and that can be solved, and you can pick your optimal energy cutoff so that these errors are similar. Okay. So in this leakage lemma that I mentioned, roughly what it states is that you can always pick your energy scale to be a little bit over your low energy of the initial state, and that depends on the parameters like X and other things. All right, so the rest of the proof is simply using some sort of union bound, and where you can show that the errors don't accumulate too much in time. Okay, so in our proof, we have also a logarithmic factor in terms of this evolution time that would diverge as time goes to 0, which seems like counterintuitive, but this seems to be just another factor of our proof, and it's not really important. It might be avoided. All right, so the next technique that I explain is this popular quantum singular value transform related to quantum signal processing, which is one of the methods of use these days for Hamiltonian simulation, and how to use it in order to improve simulation in the low energy space. So what quantum signal processing does, for example, is it takes our evolution operator here, this U of t, there's some rescaling factors, this lambda is some norm of the Hamiltonian, and first it starts from something that is called the Jacobi-Unger identity and expresses the evolution operator as just a series of Chebyshev polynomials. Okay. So these guys here are real numbers. These are the Bessel functions of first kind, and here's just a plot on how they behave. So essentially, we are trying to implement a series approximation to the evolution operator. So for some technical reasons, in quantum signal processing, we'll have to deal with an enlarged space, which means that we need to bring ancillas and so on. But again, we start from this Jacobi-Unger identity, and now we will try to emulate basically the Chebyshev polynomials by a combination of some unitaries, which are called walk operators. So of course, you have to keep track of all this, but I mean, essentially what I'm saying is that there is an approximation to the evolution operator now as a linear combination of unitary operations, okay? And those unitaries are this W to the power Q. This is called a walk operator. So, all right, so quantum signal processing of QSVT aims at implementing this series. Of course, the series has simply a number of terms. the complexity is going to depend on that number of terms. So what we'll do is to find an approximation to the evolution operator now as a final series. So we're going to put a cutoff on the degree of this linear combination of unitaries. That cutoff, Q, goes linearly in time on the norm of the Hamiltonian plus some factor that depends on the error. The next thing is that this additional factor is only logarithmic. Okay, so this exponentially improves in terms of 1 over epsilon over other methods like product formulas. So this series here seems complicated, but there is a simple gadget that you can use in order to implement it. Okay, and this is the standard QSP circuit that I show here. It's just one additional ancilla. So we do rotations in ancilla. We apply the operation W, the unitary W control to some 0 or 1 state of the ancilla, and we keep doing this. The next thing is that the number of times we need to call this unitary, this walk operator, basically goes with this Q in the series. So that Q determines really the complexity of this approach. Turns out that you can organize these spaces here, these rotation angles, such that the unitary that you implement at the end is very close to some time constant times the unitary that you wanted to prepare. Okay. So the approach is easy. It aims at implementing this linear combination of unitaries, which itself is a good approximation to the evolution operator. All right. So a little bit more of the theory side. This walk operator is usually built upon something that we call a block encoding. A block encoding is another unitary, which in one block contains the Hamiltonian. Okay. So in this model where we do have access to this block encoding, then we are good to go and implement quantum signal processing, for example, with that cost that is shown here. All right. So what is that we prove within this model? Well, it turns out that if you Hamiltonian such that is expected, for example, after the rescaling factor goes from -1 to 1, and our low energy sector is such that the eigenvalues are very close to -1, then there is an improvement over the generic cost of quantum signal processing when you simulate that states. And in fact, the complexity of our approach is this kind of strange formula here. If you remember, I mean, for quantum signal processing, we had one term which was just linear in time and the full energy scale plus some logarithmic factor. Now we replace that term by some other function of the energies of your problem, and the logarithmic factor also gets another prefactor that depends on the energy scales of the problem. And this gamma here is something that can range from delta to all the lambda, all the energy scales. So the algorithm works basically for any such gamma, and again, one can go ahead and try to optimize like what is the most efficient approach as a function of that gamma. So when you do that, right, then it's comparison between these two approaches, and you can show that there are 3 different asymptotic regimes depending on what these energies are, like how lambda compares to delta and to the error. So these are the end costs of the algorithm, okay? And when you compare for quantum signal processing, you can show that in these 2 regimes, you indeed have an improvement with respect to QSP. There's this error-nominated regime, which is not that relevant for practical applications. And there, in that case, we don't have any subdetail. All right, so very quickly, our approach goes through some other type of approximation to the evolution operator that considers some square root of the Hamiltonian. Okay, by doing so, we are able to find very good polynomial approximations to the exponential, to the evolution operator, that can be implemented more efficiently with that gadget that I did before. All right. So I have just a few minutes and make a few comments on the possibility of having more improvements, and that these algorithms showing that they are optimal and that it's not possible to get an improvement in general under this low energy assumption. So it turns out that in these papers we also prove some matching lower bounds. For each of the regimes, we have instances of problems for which basically, essentially, there's lower bounds that match the upper bounds that we have for our quantum algorithm in the low energy assumption. So these results, while here I'm showing them in terms of how many uses to the block encoding you need, actually in the paper we prove some stronger versions of this that apply to Hamiltonians which are, for example, sparse, or Hamiltonians that are given to us as a linear combination of unitaries. Those are other models that are considered within the Hamiltonian simulation literature. So, all right, and again, so typically, I mean, to see that improvement, for example, in our quantum algorithm, I made the assumption that our eigenvalues were very close to -1, right, for that to work. Usually, this is not going to happen, and you might think like, okay, well, maybe I can shift my Hamiltonian such that that condition can be met. Unfortunately, this is not possible, again, because of the generic lower bound that we have, that says that in general, unless the Hamiltonian is expressed in a particular way, then we wouldn't be able to obtain that speed up. Okay, so generally, we're unable to beat this lower bound of having a cost which is linear in time and the full energy scale of your problem. So in a similar way, we can show that the speed up from the low energy assumption is equivalent to having your Hamiltonian to be given expressed in this particular form, just as a product of two operators A and A data times some constant lambda that determines the energy scale of your problem, and assuming access to this decomposition. So in a way, roughly speaking, if you have access to kind of like the square root of the Hamiltonian, these methods are going to give you an improvement, but if you don't have such access, then there's nothing you can do in order to exploit this low energy property. Anyway, so I'm done. I try to give some overview of quantum algorithms to speed up the simulation under this low energy assumption. I explain product formulas and quantum singular value transform for these problems. I proved some matching lower bounds, so there is little room for improvement under this additional condition. But there's still room for improvement maybe in some other access models that I haven't discussed here. These techniques, of course, need to be applied to simulating systems like local spin systems, but it would be really nice to have a more general theory of low energy simulation that could apply to more complex, for example, quantum field theories. With that, I'm done. Thank you.
Thank you. Thanks very much.